tutorial. Today we're looking at a sine function. So if we have the function sine, so we'll move it over here, and it's quite an interesting example. What we're looking at here is, let's say we have sine. 1 second. Yeah, like that. Zoom in. I'll just do that. Let me just adjust the settings to give it a, yep, so that's fine. If we zoom right in, if we're going to go sine of x is equal to 2. Now, what we know about sine, obviously, is if we look at a graph, we know sine's like that. And we know sine is only between -1 and 1. You know, it's -1 is less than x, less than or equal to x, which is less than or equal to 1. So we can see immediately this is not going to be a real solution, but we can use imaginary numbers. There is actually an important identity. We know from De Moivre's theorem that e to the power of I of x is equal to cosine of x plus I sine of x. So we know that. And what we can do is we can simply substitute minus x into it to get the same formula again of e to the power of minus ix. Cosine of minus x, by the way, because cosine is the graph's basically symmetrical. It's like an even function, so therefore that's going to therefore equal. It's an even function, cosine, so it's going to just be cos. But sine is not, so you're going to have minus I sine of x. I mean, you can see that from the graphs. Look at cosine graph. It's like that, so, you know, whereas sine is like this. So you can see that the cosine is even, it's symmetrical, whereas sine is not, which is why it's like that. Now, when you get into this formula, what we can actually do is we can minus this part 1. We can do this e to the power of I of x minus e to the power of minus I of x. And basically, when you have that, the cosines are both positive, so they're going to cancel out. And then you're going to have I sine of x minus I sine of x. And that's just going to equal 2I sine of x. As a double negative is when you add. And what we can do here, so we have this now. What we can do, we can divide by 2I. And we're going to get into this format of e to the power of I of x minus e to the power of minus I of x over 2I is equal to sine of x. That's the format we have it in. Now we know from our example that sine of x is equal to 2. You know, that's what we're looking at. We're looking at when sine of x equals 2. So what we can do 2 is equal to e to the power of I of x minus e to the power of minus I of x over 2 of I. You get into this format here. And then you can very easily times both sides by 2I. And when you times both sides by 2I, you're going to have 4I equals e to the power of I of x minus e to the power of minus I of x. So you have it in that format now. Now what we can do now is we can rearrange it. There is one thing you can do which will change this. Let us rewrite this part. And let's rewrite it out to get it into a clearer format. So 4I is equal to I to the power of ix. And we know not plus. We know that e to the power of minus ix can be written as this minus 1 over e to the power of I of x. Now with this, what we can do, we can times everything by e to the power of ix. Times everything by e to the power of ix. And what you end up with is 4I e to the power of ix. We're going to actually run off the page, I apologise. We'll write it over here. But you end up, when you have that, you end up basically with 4I e to the power of ix is equal to e to the power of 2ix, apologise, 2ix minus 1, like this. Now what we can do is we can rearrange it into this format, e to the power of 2ix minus 4I e to the power of ix minus 1 equals 0. Now this is looking familiar. This is looking like quadratic. As we can write it this way, we know that e to the power of 2ix is the same thing as this squared minus 4I e to the power of ix. There's another one. minus 1 equals 0. So we have there a quadratic equation which we can solve now. What we can do is we can complete the square. That's I would say whenever you have a singular coefficient there, it's either the coefficient is 1, that's the coefficient there, it's 1 really. I mean, we haven't written it out, but that's it was the same as 1 at that. We want to just basically write it out that way. We want to, I would say whenever you have that, it's good to complete the square, as it makes things easier. So let's do that. Let's just do e to the power of I of x. And as you can see, you're going to half this term. Minus 2i squared, so in there squared. Now there's one difference. Obviously when you expand that out, you're going to get e to the power 2ix minus 4i e to the power ix, which we have. And then you're going to have the last term, but it's not going to be plus 4. It's going to be minus 4, as we know that squared, that squared is equal to minus 2 squared I squared, which is equal to 4 times by I squared. And we know I squared equals negative 1, so that's going to equal negative 4, like that. So therefore, rather than having minus 4, you're going to have, rather than having a plus 4, you're going to have a minus 4. So to get rid of that, you're going to have to actually add 4. So you're going to have it in this format of e to the power of ix minus 2i, like this, squared, and it's going to be plus 4 rather than minus 4, because usually you have minus 4 plus 4, and don't forget the minus 1 we had earlier. Minus 1 equals 0. And you're going to rearrange that into, you can rearrange it into the other side, e to the power ix minus, again it's 2i squared is equal to minus 3. Now to solve that, what we're going to do is we're going to square root both sides. So we go up here. So we're going to square root both sides. So you're going to have e to the power of I of x minus 2i is equal to, and the square root of negative 3 is going to equal I root 3, like this. And then you can get it into, and then you can rearrange it. E to the power of ix equals 2i, and also it's plus or minus, remember, plus or minus root 3. So you have it in that format there. And now I want to get into this format here, e to the power of ix is equal to I2 plus or minus root 3, like this. And then we can use we can take the natural logarithms, and we're going to get into form I of x is equal to the natural logarithm of I, and then 2 plus or equals root 3, like this. You've got the natural logarithm form now. Divide by I, divide both sides by I, we get it into x is equal to ln of I2 plus or minus root 3, like this, over I. Now remember, you can times by, what we can do is we can times by I over I, as I over I cancels to 1. So you can times by that, and you're going to get it into form, we know I times by, for the bottom, we know I times by I is equal to negative 1, and then we're going to have I on the top as well, so we're going to end up with the final form of x equals minus negative I for the natural logarithm of I, and then 2 plus or equal, and it's root 3. Now this itself can actually be simplified even further. What we want to do is, we know inside here, these parts here, basically, in logarithms, that they are timesing together, aren't they? They are timesing, which means you can write it into form, with logarithms, you can write it into a form of x is equal to negative I, and let's put in brackets, we can split it up, break it up into I plus ln of 2 plus or minus root 3. So we have it in this form now. Now there's one thing we want to look at now. With that form, with that form that we have it in now, what we want to look at now is that we know that I'm going to look at an identity, ln of I, right? Let's write that as e to the power of y. It's a terrible y, I apologize. It's still a terrible I apologize. Equals I. Now we know again from De Moivre's theorem that e to the power of ix is equal to cosine of x plus I of sine of x. Now what we're going to do, we're going to choose x equals pi over 2, and you're going to see why. When we do that, it's going to be e to the power of pi over 2 times by I is equal to cosine of pi over 2 plus I sine of pi over 2. Now what does that equal? Well, we know pi over 2, cos of pi over 2 is going to be 0, and sine of pi over 2 is going to equal not 0, sorry, 1. In other words, it's going to equal I. We know therefore that e to the power of pi over 2I is equal to I, which is pretty interesting. So therefore we know, with this we can basically do the next part, which is that, is that we can now very easily now change that now. So we know basically that y, which is ln of I, is equal to pi over 2I. So therefore, x is equal to negative I pi over 2I, like that, plus ln of 2 plus or equals root 3, like this. And that's the form that we have it in now. And with this form, you can expand it out. When you expand it out, you're going to get x is equal to negative pi over 2 I squared, as it's I times I, and minus ln, the natural logarithm, of 2 plus or equals root 3 times by I. That is the format that you're going to get it into. And to fully solve that, we know that I squared there is equal to negative 1. So therefore negative 1 times by minus pi over 2, like this. X, that's not very good. Therefore x, sorry I keep getting it wrong. X equal to pi over 2 minus I ln of 2 plus or equal root 3. So you got into that format there. Now this here, you see it's a complex number. You've got the two parts. Remember, complex numbers are written as a plus bi. And we know therefore that a is equal to, and in this case a is equal to pi over 2 and b is equal to ln of 2 plus or equal root 3. And that is the format you get it into, and it's important to look at that. And this is now very useful. It's something we can actually use, and I think, and if you're, you could now plot that on the complex plane. And this is a good form now I've got it into. And this is something you can get with complex numbers. We know therefore sine of this complex number, which is called a plus I of b. It's not very clear, but we know that. I apologize. Of I of b. I don't know why I'm doing that. So sorry. Of I of b, like that, equals 2 when a and b are equal to those. When a equals is when a is equal to pi over 2, and when b is equal to negative ln of 2 plus or equals root 3. And yeah, it's pretty. This is where complex numbers is pretty useful. You can do pretty interesting things with them. And you can solve things that seem that they can't be solved. When people say there's no real solutions, it doesn't mean that there's no. You can have these imaginary solutions to a lot of things, and quite a lot of examples you can solve. I mean, you can even solve things like things like this can be solved with negative numbers. With imaginary numbers. You can have negative numbers from exponents with imaginary numbers. It does make things very interesting and unique. So it's definitely worth looking into. But yeah, I hope that helps. And again, it's always good fun. This is sort of like a maths for fun series. We are looking at mechanics in this series, but we also want to look at other things, other kinds of mathematics like calculus and just general maths, because we're very into that. But yeah, please do consider subscribing, and thanks for watching.